A mile beneath the Pacific, the ocean floor is rising. Right now, it sits higher than it has ever stood in recorded history. This is Axial Seamount, the most closely watched volcano hidden under the Pacific Ocean, and it has crossed a line scientists have never seen it cross before. Today we drop into a world with no sunlight, where the seafloor breathes like a living thing. You will meet creatures built for boiling water, ride alongside robots built for crushing pressure, and stand at the edge of a crater that swallowed itself in 2015. Scientists built a model just to catch what this mountain does next. If mysteries like this pull you in, tap subscribe. It genuinely helps this channel grow. Take a breath. The volcano already has. We begin. 300 miles off the coast of Oregon, something under the ocean is moving. Not a wave, not a current, the seafloor itself. A mile down, past the reach of sunlight, past the reach of almost every submarine on Earth, a mountain is quietly rising. Scientists have been watching it happen for years, one careful measurement at a time, and now, for the first time since anyone started counting, the ground down there sits higher than it has ever stood before. This is Axial Seamount, and it is the most closely watched volcano hiding under the Pacific Ocean. Reaching it takes almost a full day by research ship, sailing straight out from the Oregon coast into open water with nothing but waves in every direction. Down at the seafloor, the water sits barely above freezing, crushed under pressure roughly 200 times heavier than what your body feels standing on a beach. No storm on the surface, no tide, nothing a person could ever notice from a boat gives away the fact that an entire mountain, a mile below, is swelling like a bruise. You will never see it from a boat. You will never see it from a plane. The ocean above it looks calm, blue, empty, exactly like every other patch of open water along the west coast. But underneath that calm surface, magma is pushing upward, inch by inch, filling a hidden chamber of melted rock the size of a small city. Picture a balloon slowly filling with air under a rug. From the top, the rug looks flat. Nothing seems wrong. But underneath, the pressure keeps building, and eventually something has to give. That is what has been happening at Axial Seamount for more than 10 years. Scientists first caught this volcano erupting in 1998. It surprised almost everyone. Then it erupted again in 2011. And in 2015, something remarkable happened. Researchers predicted the eruption before it started. For the first time in the history of volcanology, a team looked at the data, made a call, and watched the ground do exactly what they said it would. Since that eruption, the volcano has been quietly refilling itself, like a lung slowly breathing back in. By the end of 2024, it had climbed back to about 95% of the height it reached right before the 2015 eruption. Everyone expected the next blast to come fast. Instead, the volcano stalled. The shaking that usually comes before an eruption barely showed up. Scientists waited and waited. Then, without warning, the ground kept climbing anyway. Today, the seafloor above Axial Seamount sits about 4 inches higher than the exact level it reached just before its last eruption. 4 inches might not sound like much, but picture stacking 4 cell phones on top of each other, flat on a table. Now imagine an entire section of ocean floor, wider than a football field, lifted by that same amount, all at once, all from pressure building somewhere no human has ever touched. Nobody has ever seen this volcano stand this tall. Every past eruption gave scientists a line in the sand, a level they thought marked the breaking point. Axial Seamount just walked straight past that line and kept going, which raises a question nobody can answer yet. If the old warning signs no longer apply, what happens when this mountain finally lets go? Somewhere beneath every ocean on Earth, mountains taller than anything on land are hiding in plain sight. Scientists call them seamounts, and Axial Seamount is only one of tens of thousands scattered across the ocean floor. A seamount is simply an underwater volcano, built the same way a mountain on land gets built, layer by layer of hardened lava, except almost nobody ever sees it happen. Most seamounts never break the surface. They rise from the deep ocean floor, climb thousands of feet, and stop just short of daylight, buried under a mile or more of freezing, crushing water. Axial Seamount stands roughly a mile tall, yet its summit still sits well below any wave, any boat, any beam of sunlight strong enough to reach it. Think about the tallest building you have ever seen. Then imagine stacking 4 of them on top of each other. That gets you close to how far down the water goes above this volcano's peak. For most of human history, mountains like this simply did not exist to us. We had no way to look. Ships could sail directly over the top of an active volcano and never know it was there. The ocean kept its secret simply by being too deep, too dark, and too dangerous to explore. That changed once scientists built tools that could see without light. Sonar sent sound waves bouncing off the seafloor, mapping shapes no human eye had ever traced. A ship would ping the bottom of the ocean, wait for the echo to bounce back, and use the timing to calculate exactly how far down the seafloor sat at that single point. Do that enough times, across enough miles, and a blurry picture slowly sharpens into an actual map, mountain by mountain, ridge by ridge. Slowly, an entire hidden mountain range came into focus, stretching along the edges of tectonic plates like a scar running across the bottom of the sea. Axial Seamount turned out to be one of the most active spots on that entire hidden map. It sits directly on top of what scientists call a hotspot, a place where a plume of extra hot rock rises from deep inside the planet and pools just beneath the crust. Combine that hotspot with a crack already forming in the seafloor, and you get a volcano with an unusually steady, unusually generous supply of melted rock feeding it from below. Most seamounts stay quiet for thousands, sometimes millions of years. Axial Seamount does not behave that way. It erupts on a human timescale once every decade or so, which makes it one of the very few volcanoes on the entire ocean floor that scientists can actually study while it happens. That is the reason a mile of freezing water has not managed to keep this mountain a secret. Compare that to a typical seamount, one that might erupt once every few 100,000 years. A scientist studying that kind of volcano could spend an entire career watching nothing happen at all, gathering data on a system too slow to ever reveal its secrets within a single human lifetime. Axial Seamount offers something almost nowhere else on the ocean floor can, a genuine chance to watch a volcano's entire life cycle unfold across a career instead of an eon. But being reachable is not the same as being safe to reach. To understand why finding this volcano barely mattered compared to what came next, you have to look at exactly where on the map it happens to sit. Zoom out far enough, and Axial Seamount stops looking like a lone mountain and starts looking like one tiny piece of a much bigger, much stranger pattern. Draw a horseshoe around the entire Pacific Ocean, tracing the coastlines of Japan, the Philippines, New Zealand, Chile, and the western edge of North America, and you have just traced what scientists call the Ring of Fire. It is not an actual ring of fire in the way it sounds. It is a chain of cracks and collisions in the Earth's crust, stretching roughly 25,000 miles, about the same distance as circling the entire planet at the equator. Along that single chain sit around 3 out of every 4 active volcanoes on Earth. That is not a coincidence. The Ring of Fire exists because giant plates of rock, the same plates that carry entire continents and oceans, are constantly grinding, splitting, and diving beneath each other around the Pacific Basin. Wherever plates collide or pull apart, melted rock finds a path upward, and a volcano is born. Picture the crust of the Earth as the cracked shell of a hard-boiled egg, except every piece of that shell is slowly sliding around on a layer of much hotter material underneath. Around the Pacific, those shell pieces happen to meet at more edges, more often than almost anywhere else on the planet. Some of the most famous eruptions in recorded history happened along this same ring. Mount St. Helens, Krakatoa, Mount Pinatubo, each one reminded the world just how much power sits coiled beneath the Pacific's surface. Millions of people live within sight of a volcano somewhere along this same chain, in cities stretching from Tokyo to Seattle to Santiago. Most of them going about ordinary days without a single thought about the restless ground beneath their feet. Axial Seamount sits on this same ring, but in one of its quieter, less understood corners, hidden underwater where nobody has to evacuate a city or watch ash fall from the sky. That is exactly what makes it so valuable to scientists. They can study a genuinely active, genuinely dangerous volcanic system without putting a single town at risk. Recent years have only made this ring feel busier. Monitoring agencies across the Pacific, from Japan's earthquake network to observatories in Alaska and Indonesia, have logged unusually high numbers of earthquakes and eruptions in the past couple of years alone. Dozens of separate volcanoes have shown fresh activity within the same short stretch of time, some erupting for the first time in living memory. Nobody claims to know exactly why activity has picked up in so many places at once. What scientists do agree on is that the Ring of Fire has never stopped being one of the most dangerous, most closely watched features on the entire planet, and every fresh burst of activity gives researchers another reason to keep their instruments running around the clock. Volcanologists studying the Ring of Fire often compare it to a patient with a racing pulse. Dozens of separate systems all tied to the same underlying cause, plates constantly shifting against each other around one enormous ocean basin. Somewhere within that enormous, restless ring, one particular stretch of seafloor happens to be splitting apart in slow motion, 1 millimeter at a time. That crack has a name, and it runs directly beneath the volcano this story keeps circling back to. Off the coast of Oregon, two enormous slabs of the Earth's crust are pulling apart from each other, so slowly that nobody standing on a boat above them would ever notice. Scientists call this crack the Juan de Fuca Ridge, and it runs like a seam along the bottom of the Northeast Pacific. On either side of that seam sit two tectonic plates, gigantic sheets of rock that make up the outer shell of the planet. Every year, those two plates drift apart by about 2 inches, roughly the same distance your fingernails grow in a year. 2 inches sounds tiny. Multiply it across millions of years, though, and that small yearly gap has carved an entire mountain range along the ocean floor, one of the longest volcanic chains on Earth, most of it never seen by a single human eye. Here is the part that matters most for axial seamount. Whenever two plates pull apart like this, they leave a gap behind them. Deep underground, melted rock rises to fill that gap, the same way water rushes in to fill a hole dug at the beach. That rising rock is magma, and along the Juan de Fuca Ridge it is constantly working its way upward, cooling into fresh new ocean floor the instant it touches cold seawater. Axial seamount sits directly on top of this spreading ridge, at a spot where the crack in the crust happens to line up with an extra deep, extra steady source of magma rising from far below. Think of it like a garden hose with a slow, steady drip, except the drip is molten rock, and it has been filling the same underground chamber for longer than anyone has been alive to measure it. That combination, a spreading ridge plus a hotspot of extra magma, is rare. Most of the volcanic activity along mid-ocean ridges happens quietly, spread out over enormous distances, with no single peak rising high enough to matter. Axial seamount breaks that pattern. All that magma pools in one place instead of spreading thin, building a genuine mountain instead of a low, flat scar. This is also why the volcano keeps inflating and deflating in such a measurable, almost rhythmic way. As magma pushes into the chamber beneath it, the seafloor above physically lifts, like dough rising in an oven. When enough pressure finally builds, the ground cracks, lava escapes, and the whole area sinks back down again. Most volcanoes on land depend on a tangle of overlapping factors, shifting weather, groundwater, gas pressure, human activity nearby, that make their behaviour messy and hard to read. Axial seamount sits in near total isolation, untouched by rainfall, untouched by roads or cities, with almost nothing disturbing the steady push of magma from below. That isolation is exactly what makes its rhythm so unusually clean to measure, closer to a laboratory experiment than the chaos of a volcano surrounded by roads, forests and shifting weather on the surface. Scientists sometimes describe the Juan de Fuca Ridge as one small piece of a much larger system, a network of similar spreading ridges that stretches across nearly every ocean basin on the planet, quietly building new seafloor everywhere it goes. Scientists did not stumble onto this pattern by accident. Understanding it took decades of ships, sound waves, and stubborn curiosity about a stretch of ocean most people will never think about twice. That search for answers eventually led researchers to something they were not fully prepared for. For a long time, axial seamount was just a bump on a map, one shape among thousands of unnamed peaks scattered across the ocean floor. Ships mapping the Juan de Fuca Ridge in the 1970s and 80s used sonar to trace the shape of the seafloor, sending sound waves down into the dark and timing how long they took to bounce back. Slowly, point by point, a picture formed. A broad, rounded volcano rising about a mile above the surrounding seafloor, with a wide, sunken crater at its summit called a caldera. At first, nothing about it screamed danger. Plenty of extinct volcanoes look exactly like this, quiet mountains that stopped erupting millions of years ago and simply sat there ever since. Then researchers dropped instruments onto its slopes and found something that changed everything: heat. Enormous plumes of scalding, mineral-rich water were pouring out of cracks near the summit, staining the surrounding rock black and orange. That heat meant one thing. Somewhere beneath this mountain, magma was still very much alive. Submersibles eventually carried scientists down for a first-hand look, tiny submarines built to survive pressure heavy enough to crush a car. Riding down took more than an hour, sinking through water that shifted from bright blue to deep green to total blackness long before the seafloor ever came into view. Through thick, round windows, researchers watched towers of mineral rock rising from the seafloor like chimneys, pouring out water hot enough to warp metal. They found fields of strange, pale creatures clustered around those chimneys, living entirely on chemicals instead of sunlight, in numbers nobody expected to find so far from any source of daylight. This was not a dead mountain. It was an active volcanic system, alive and breathing, hidden a mile beneath one of the busiest coastlines in the country. What sealed axial seamount's reputation, though, was catching it in the act. In 1998, instruments recorded a sudden dramatic drop in the seafloor near the summit, along with a burst of thousands of small earthquakes. The volcano had erupted, spilling fresh lava across the caldera floor, and nobody had predicted it. Scientists reviewing the data afterward described the feeling as equal parts thrilling and humbling, proof that a mountain they had only just started to understand still had the power to surprise everyone watching it. That surprise turned axial seamount from an interesting mountain into one of the most important natural laboratories on the planet. If this volcano could erupt again, and clearly it could, then it offered something almost no other volcano on Earth could: a chance to watch an eruption build in real time without a single life at risk, using instruments left permanently on the seafloor. For a field used to studying disasters only after they happened, that possibility felt almost unheard of. Scientists began wiring the volcano with sensors, determined never to be caught off guard again. Every follow-up expedition added another piece to the picture, another instrument, another year of baseline data, slowly turning a single surprising eruption into the foundation of an entirely new way to study volcanoes. What they built next would turn this lonely underwater mountain into one of the most closely monitored places on the entire planet. And it started with something most people have never heard of: chimneys that breathe fire made of water. Picture a chimney built entirely by nature, standing on the ocean floor pouring out water hot enough to melt lead. That is a black smoker. An axial seamount is covered in them. Deep inside the volcano, seawater seeps down through cracks in the rock and gets trapped near the magma chamber below. There, it heats up dramatically, sometimes reaching temperatures above 700 degrees Fahrenheit, hot enough to melt certain metals on contact. Normal water would boil away instantly at that temperature. This water stays liquid because the crushing pressure of the deep ocean, more than 200 times the pressure at sea level, keeps it from turning into steam. Without that pressure holding everything together, the entire process powering these chimneys simply could not exist anywhere closer to the surface. As that superheated water rushes back up through cracks in the seafloor, it picks up dissolved minerals along the way: iron, copper, zinc, and sulfur, pulled straight out of the surrounding rock. When it finally blasts out into the freezing ocean above, the sudden temperature change causes those minerals to crystallize almost instantly, turning the escaping water pitch black and solid enough to build structures. Over years, those mineral particles stack on top of each other, chimney after chimney, some growing taller than a two-story house. Black smokers at Axial Seamount have names, given by the scientists who study them again and again, the same way explorers name landmarks on a familiar trail. Some chimneys have stood tall enough, long enough, that researchers have watched them grow year over year across an entire career, then collapse or vanish within a single eruption, buried under fresh lava overnight. The scene around these chimneys looks almost otherworldly. Clouds of dark, mineral-rich water billow upward like smoke from a chimney on land. Except this smoke is liquid, rising into freezing seawater that never sees a single ray of sunlight. Around the base, strange creatures cluster in surprising numbers, drawn to warmth and chemicals most life on Earth would consider poison. A single dive past one of these chimneys can feel like stepping onto an entirely different planet, one lit only by the glow of instruments and the occasional flash of a camera. This matters for more than just the strange scenery. Black smokers act like pressure valves for the volcano, releasing heat and fluid from deep underground before it has a chance to build to dangerous levels in one single spot. Scientists track changes in the temperature and chemistry of this water closely, because shifts often hint at changes happening in the magma chamber far below. When Axial Seamount is getting ready to erupt, these vents sometimes behave differently, running hotter or shifting in chemistry. Small clues in an underwater detective story most people will never hear about. Researchers sample this water on nearly every expedition, storing it in sealed containers and hauling it back to laboratories on shore, where its exact chemical makeup can reveal changes invisible to any camera. A shift in a single dissolved gas can hint at fresh cracks opening deep underground, long before any instrument on the surface detects change. Chimneys pouring out water hot enough to melt lead would be strange enough on their own. What makes this deep ocean world even stranger is what has managed to make a home there, thriving in conditions that would kill almost anything else on the planet within seconds. No sunlight reaches the bottom of the ocean above Axial Seamount. No plants grow there. No photosynthesis powers a single living thing. And yet, crowded around the black smokers of this volcano, life thrives in staggering numbers. Giant tube worms cluster together in white, fleshy colonies, some growing taller than a kitchen counter, with no mouth, no stomach, and no eyes. Instead, they rely on bacteria living inside their own bodies, bacteria that survive by feeding on chemicals dissolved in the volcano's scalding water. The worms essentially farm their food from the inside out, turning poison into energy the way a plant turns sunlight into sugar, a trick that took biologists years of careful study to fully piece together. Nearby, colonies of blind shrimp swarm the base of the chimneys by the thousands, packed so tightly they look like a shifting carpet. With no working eyes in a world with no light to see by, these shrimp instead sense heat directly, using specialized patches on their backs that can detect the faint glow given off by the volcano's superheated water. Giant clams the size of dinner plates wedge themselves into cracks near the vents, filtering chemicals from the water instead of the usual plankton most clams rely on. Pale crabs pick their way across fields of mineral rock, scavenging whatever drifts close enough to reach. Even octopuses have been spotted wandering this deep, hunting through a landscape that looks more like the surface of another planet than anywhere on Earth. None of this life could survive anywhere else on the surface world. The water around these vents can shift from near freezing to scalding within the space of a few feet. The chemicals pouring out would poison almost any other creature on Earth, and the pressure alone, heavy enough to crush a submarine's hull if something failed, would kill an unprotected human being in seconds. Every creature living around these vents has spent countless generations adapting to exactly these extremes, in a place where the normal rules of survival simply do not apply. When scientists first found ecosystems like this in the 1970s, at a different set of vents near the Galapagos Islands, it reshaped an entire branch of biology. For the first time, researchers had proof that life did not need sunlight at all. It only needed energy, and chemicals pouring out of the Earth itself could provide exactly that. Axial Seamount became one of the best natural laboratories on the planet for studying this kind of life, because scientists could return to the exact same vents year after year and watch entire communities grow, shift, and sometimes vanish overnight. Biologists studying these creatures have compared the experience to checking on a garden that grows in complete darkness, using nothing but heat and chemistry instead of sunlight and rain. That last part matters more than it might sound, because when this volcano finally erupts, lava does not just reshape the seafloor, it can wipe out an entire thriving ecosystem in minutes, only for something even stranger to grow back in its place, often within weeks, as fresh vents open and new colonies rush in to claim the warm, chemical-rich water pouring out. Before any of that can happen again, though, scientists first had to figure out how to watch this volcano without ever leaving dry land. Sending a submarine down to check on a volcano every single day was never going to work. Submersibles are expensive, slow, and can only stay underwater for a few hours at a time. If scientists wanted to actually catch an eruption happening in real time, they needed something that never had to come back up for air. The answer was cable, a lot of it. Starting in the 2010s, researchers began laying down what became known as the Regional Cabled Array, a network stretching more than 660 miles of fiber optic and power cable across the seafloor off the coast of Washington and Oregon. Picture running an extension cord from the middle of a city all the way out past the horizon, then down a mile underwater, then across an entire volcano. That cable connects more than 140 separate instruments, scattered around axial seamount and the surrounding ridge. Cameras, seismometers that detect the faintest tremors, pressure sensors capable of noticing the seafloor shifting by a fraction of an inch, chemical sensors that sniff the water pouring out of black smokers, tracking changes nobody could see with the naked eye. Together, this network turns an entire underwater volcano into something closer to a hospital patient, hooked up to constant monitoring, every vital sign tracked and recorded without a single gap. Every single one of those instruments sends its data racing back to shore at the speed of light, the same way information travels through the internet cables that carry a video call across an ocean. Scientists sitting in offices in Oregon can pull up a live feed from a volcano a mile underwater and 300 miles offshore, almost as easily as checking the weather app on a phone. This changed everything about how axial seamount could be studied. Instead of occasional snapshots taken during rare, expensive ship expeditions, researchers suddenly had a live, continuous stream of information 24 hours a day, every day of the year. A tremor at 3 a.m. no longer had to wait weeks to be noticed. It showed up on a screen within seconds, sometimes waking up a scientist checking data from home on a laptop. Building a system like this a mile underwater came with enormous challenges. Every cable, every connector, every instrument had to survive crushing pressure, near freezing temperatures, and constant exposure to corrosive seawater, all while staying reliable enough to run for years without maintenance. Engineers essentially had to build a small permanent city's worth of wiring at the bottom of the ocean and expect it to just keep working, with no easy way to send a repair crew down if something failed. It did. And once that wiring was in place, scientists finally had exactly what they needed to answer a question that had frustrated volcanologists for generations. Could anyone ever actually see an eruption coming before it happened? Engineers, biologists, and volcanologists all had to work together to design a system that could serve every kind of science at once, a rare kind of teamwork for a project buried a mile underwater. The tool that would end up answering the biggest question of all was smaller than almost anything else on the entire cabled network, and far more precise than anyone expected. Somewhere on the summit of axial seamount sits an instrument that can detect the ocean floor rising by less than the thickness of a stack of coins. It is called a bottom pressure recorder, and it works on a surprisingly simple idea. Water pressure increases the deeper you go. So if the seafloor itself rises, even slightly, the instrument sitting on top of it ends up a tiny bit closer to the surface, and the water pressure pushing down on it drops by a tiny measurable amount. That is the entire trick. Measure pressure closely enough, and you can measure the ground rising underneath you without ever touching a ruler to the seafloor. These sensors are sensitive enough to detect ground movement as small as a fraction of an inch. Scientists have compared it to trying to measure how much a sidewalk lifts when a single ant walks across it. Except instead of an ant, The thing being measured is an entire underground chamber of molten rock pressing upward from below. That level of precision took years of careful engineering to achieve, since even small changes in temperature or ocean current could throw off a cruder instrument entirely. Several of these recorders sit scattered across Axial Seamount's caldera floor, feeding a steady stream of data back through the regional cabled array every single day. Plotted on a graph, the pattern looks almost like a heartbeat. Slow, steady inflation for months and years at a time, then a sudden, sharp drop the instant an eruption drains the magma chamber below. Scientists cross-check this data constantly, comparing readings from multiple recorders spread across different parts of the caldera floor at once. If every instrument tells the same story, researchers can trust the pattern. If one sensor disagrees with the rest, it usually means something local, a shifting rock, a stuck cable, rather than a genuine change in the volcano itself. After the 2015 eruption, the seafloor above Axial Seamount dropped suddenly, then began climbing again almost immediately, like a lung slowly filling back up after being emptied. Scientists watched that climb continue for years, tracking every inch with instruments precise enough to catch the smallest hiccup in the pattern. That steady climb is exactly what let researchers do, something volcanologists had struggled to do anywhere else on Earth: predict an eruption in advance. By comparing the current rate of inflation to the pattern that came before the 2015 eruption, scientists could estimate roughly when the ground might reach a similar danger point again. For years, that method worked well enough to build real confidence, turning a simple pressure reading into one of the most trusted tools in the entire field of volcano forecasting. Then, starting around 2024, the pattern stopped behaving the way anyone expected. The ground kept rising. But instead of levelling off near the old danger line the way it had before past eruptions, it just kept going, climbing past every previous benchmark scientists had ever recorded. It was the first time in the volcano's monitored history that the climb had continued this far past a previous benchmark without any sign of slowing down. To understand exactly how strange that is, you first have to see what happened the last time this same instrument caught the volcano finally letting go. In January of 1998, instruments scattered across the seafloor near Axial Seamount recorded something nobody had planned for: a sudden burst of activity that arrived with almost no warning anyone at the time knew how to read. Thousands of small earthquakes, one after another, rattling through the rock in a pattern scientists call an earthquake swarm. Within days, the pattern grew intense enough that researchers scrambled to get a ship out to the site, uncertain exactly what they were racing toward, working off nothing but a handful of distant readings and a growing sense that something big was already underway. What they found once instruments reached the seafloor told the story clearly. A section of the caldera floor had dropped by several feet almost instantly. Fresh lava, still warm from the depths of the Earth, coated large sections of the summit. Axial Seamount had erupted, and it had done so without a single clear warning sign that scientists at the time knew how to read. This was not entirely surprising. In the late 1990s, monitoring an underwater volcano in real time was still a fairly new idea. Most of the instruments scientists relied on to detect earthquakes sat on land, hundreds of miles away, straining to pick up faint signals travelling through miles of rock and water. Catching the exact moment of an eruption a mile underwater before it happened was closer to science fiction than established science. Even after the fact, confirming what had happened took real effort. Ships had to sail out, lower instruments through more than 5,000 feet of open water, and carefully compare new seafloor images against maps drawn years earlier. There was no live video feed, no instant alert, just patient, careful detective work spread across weeks, piecing together a story that had already finished playing out days before anyone arrived to witness the aftermath. Still, the eruption became a turning point. It proved beyond doubt that Axial Seamount was not some ancient sleeping mountain. It was an active volcanic system, capable of dramatic, sudden change, sitting directly beneath a stretch of ocean that commercial ships crossed every single day. More importantly, it gave scientists their first real before and after picture. Comparing seafloor surveys taken before the eruption to surveys taken afterward let researchers measure exactly how much the ground had dropped and exactly how much lava had spread across the caldera floor. For the first time, An active submarine eruption had left behind a clear, measurable fingerprint, something researchers could study for years afterward. That fingerprint became the foundation for everything that came next. If scientists could measure how the ground behaved after an eruption, then maybe, with enough patience and enough instruments, they could learn to recognize the warning signs building up before one. It was a slow, unglamorous kind of science, mostly patience and repetition, the sort of careful groundwork that rarely makes headlines on its own. It would take more than a decade of careful, unglamorous monitoring work before anyone felt confident enough to test that idea for real. And when they finally did, axial seamount would once again be the volcano that made history, this time for entirely different reasons. No longer just the volcano that surprised everyone, but the one that taught scientists how to stop being surprised. By the time April of 2011 arrived, scientists had spent more than a decade quietly building a case for how axial seamount actually behaves. Ever since the surprise eruption of 1998, researchers had kept instruments running on the seafloor almost continuously, tracking the slow, steady rise of the ground above the volcano's magma chamber. Year after year, the seafloor climbed patiently, predictably, the way water fills a glass left under a slow, steady drip, with almost nothing to interrupt the pattern. Then, in April of 2011, the ground suddenly dropped again. This time, scientists were far better prepared to notice. Instruments picked up a sharp burst of earthquakes in the hours before the collapse, followed almost immediately by a measurable drop in seafloor pressure, the unmistakable signature of an eruption draining the magma chamber below. Researchers scrambled a ship to the site within days, eager to compare fresh data against everything they had learned since the last eruption. This time, nobody was caught completely off guard, a small but meaningful difference from the confusion of 1998. What they found confirmed something researchers had started to suspect. The volcano appeared to follow a rough, repeating rhythm. Magma refilled the chamber beneath it at a fairly steady pace. The seafloor rose in response, and once the ground reached roughly the same height it had reached before the previous eruption, the volcano tended to let go again, almost like clockwork. That single observation changed how scientists thought about axial seamount completely. If the pattern held, then measuring the height of the seafloor might actually work as an early warning system. Not a perfect one, but a genuine, testable one. It felt almost like discovering that a stove clicks the exact same way every time right before it catches fire. A small, repeatable clue hiding inside a process that once seemed completely random. Researchers Bill Chadwick and Scott Nooner, who had been tracking this volcano for years by this point, began sketching out an idea that sounded almost reckless to some of their colleagues. What if they used this inflation pattern to predict the next eruption before it happened? Publicly, on the record, instead of only explaining events after the fact, the way most volcanologists preferred to work. Volcanologists had rarely attempted anything like this anywhere else on Earth. Most volcanoes are far too unpredictable, shaped by too many overlapping factors to trust a forecast made years in advance. Axial seamount, hidden beneath the ocean and largely undisturbed by the chaos of daily human activity, offered something rare, a natural laboratory clean enough to actually test the idea properly. Colleagues at conferences reportedly questioned whether the two researchers were being too bold, warning that a failed public prediction could set the entire field back. The seafloor above the volcano began climbing once again, almost immediately after the 2011 eruption. Scientists watched it rise month after month, comparing every new measurement against the pattern from years before. Every fresh reading from the seafloor either strengthened that confidence or threatened to unravel it entirely, and for a long stretch of years, the numbers kept lining up in exactly the way the two scientists hoped they would. They did not have to wait long to find out whether their theory actually worked. By late 2014, the ground above axial seamount had climbed to nearly the same height it reached right before the 2011 eruption. Bill Chadwick and Scott Nooner had been waiting for exactly this moment. Based on years of careful measurement, they made a bold public prediction. Axial seamount would very likely erupt sometime before the end of 2015. Making a forecast like that took real nerve. Volcanologists rarely commit to a specific window months in advance, because getting it wrong publicly can be embarrassing, and getting it wrong scientifically can undermine an entire method. If axial seamount stayed quiet, the whole idea of forecasting eruptions through inflation patterns would look far shakier to the rest of the scientific community. The volcano did not stay quiet. On April 24, 2015, instruments detected a massive swarm of earthquakes ripping through the seafloor near the summit, more than 8,000 tremors within a single day. Seafloor pressure sensors recorded a sudden dramatic drop, the clearest sign possible that the magma chamber below had emptied and the caldera floor had collapsed downward. Scientists watching the live data feed that day described it as one of the most exciting moments of their careers, watching a prediction made months earlier come true in real time on the screen in front of them. Axial seamount had erupted almost exactly when Chadwick and Nooner said it would. For the field of volcanology, this mattered enormously. Predicting the eruption of a land-based volcano is difficult enough, with dozens of overlapping factors like gas emissions, ground swelling, and shifting earthquake patterns all pulling in different directions at once. Successfully forecasting an eruption months in advance, based mainly on one clean, steady signal, ground inflation, had never been done with this level of confidence anywhere on Earth. Lava from the eruption spread across large sections of the caldera floor, reshaping the underwater landscape scientists had mapped so carefully for years. Some of the black smoker chimneys researchers had studied for over a decade were buried entirely. New vents opened elsewhere. Entire communities of tube worms and blind shrimp were wiped out in places, only for fresh colonies to begin forming again within months, feeding off chemicals released by the freshly cooled lava. Researchers returning to the site described it almost like visiting a familiar neighbourhood after a flood, recognisable in outline but rearranged in nearly every detail. Landmarks they had photographed for years were simply gone, replaced by fresh black rock still cooling from the inside. The success of this prediction turned axial seamount from a fascinating case study into something closer to a proving ground. If scientists could learn to read this one volcano well enough to call its next move, maybe the same careful, patient approach could eventually help forecast far more dangerous volcanoes, ones sitting directly beneath cities instead of a mile under empty ocean. News of the successful call spread through the scientific community quickly, cited for years afterward as proof that eruption forecasting was not just possible, but repeatable. For a while, it looked like scientists had finally cracked the code on one of nature's most stubborn puzzles, a repeatable formula for predicting when the ground itself would break open. There was just one problem waiting on the horizon. The exact method that worked so well in 2015 was about to run into a version of this volcano that refused to follow its own rules. Ever since the successful forecast of 2015, one question has followed Bill Chadwick everywhere. Can he do it again? Chadwick, a researcher at Oregon State University's Hatfield Marine Science Center, has spent years running the numbers on axial seamount, alongside his longtime collaborator Scott Nooner. Together, the two of them maintain a public blog dedicated entirely to tracking this one volcano, posting updates whenever new data shifts their thinking, sometimes admitting openly when their own predictions turn out to be wrong. Few scientists anywhere invite that level of public scrutiny onto an active, ongoing prediction. That kind of public honesty is rare in science. Most researchers publish results only after they know the outcome, carefully polished, safely confirmed. Chadwick and Nooner have done the opposite, laying out their reasoning in real time, forecast by forecast, letting anyone with an internet connection watch them try to solve one of the hardest puzzles in volcanology in full public view. Students, teachers, and curious strangers from around the world have followed along for years, refreshing the same blog the way some people check sports scores. Following the 2015 eruption, the two scientists expected their method to work roughly the same way it had before. Track the inflation, compare it to the pattern from past eruptions, estimate a window. By late 2024, the seafloor had climbed to about 95% of the height it reached just before the 2015 event, and forecasts pointed toward an eruption sometime around the end of 2025. Confidence in the method had rarely felt higher. Then the volcano stopped following the script entirely. Chadwick has openly compared what happened next to a familiar sports narrative, a team expected to win easily that suddenly, unexpectedly stalls right before the finish line. Inflation slowed sharply in early 2025. Worse, the earthquakes that typically accompany rising pressure barely showed up at all, staying far below the levels seen before past eruptions, leaving researchers with a puzzle instead of a countdown. By October of 2025, Chadwick updated the blog with an admission familiar to anyone who has ever watched a forecast fall apart in real time. The timeline needed revising, likely pushing any eruption into the middle or later half of 2026. He wrote plainly that nearly every forecast made since the last eruption had needed adjusting at some point, a level of honesty rarely seen from a scientist in the public eye. What makes this moment different from every previous stall is what came next. Instead of levelling off near the old danger line the way it had after previous eruptions, the ground kept rising anyway, eventually climbing past the exact height it stood at before the 2015 eruption altogether. Chadwick has spent his career trying to teach this volcano's rhythm to the rest of the world, turning a stubborn, hidden mountain into one of the best understood volcanoes on the planet. Right now, for the first time in years, even he is watching it do something the data alone cannot fully explain. To understand why the old rulebook stopped working, it helps to look at a volcano on the opposite side of the planet that taught scientists this exact lesson first. Strip away all the instruments and technical terms, and axial seamount behaves a lot like something far more familiar: a lung. For years at a time, the volcano slowly inflates. Magma rises from deep within the earth, pooling in a chamber roughly a mile beneath the caldera floor, gradually pushing the ground above it upward. This process happens patiently, a fraction of an inch at a time, day after day, with no dramatic warning, no sudden jolt, just a slow, steady climb that instruments on the seafloor track constantly. Then, once enough pressure builds, everything changes within hours. Cracks finally give way somewhere in the surrounding rock. Magma rushes upward and outward, escaping through fissures in the seafloor as fresh lava. The chamber below empties rapidly, and the ground directly above it, no longer supported by that underground pressure, drops suddenly, sometimes by several feet, in a matter of hours rather than years. Instruments that had recorded nothing but a slow, steady climb for a decade suddenly show a nearly vertical drop on the graph within a single day. Picture blowing up a balloon slowly over the course of an entire afternoon, only for someone to pop it in a single instant. Axial seamount runs through a version of that same cycle, except the inflating stage stretches across years instead of minutes, and the collapse plays out across a section of ocean floor wider than a football field. The entire caldera floor can drop several feet within a matter of hours, an amount of sudden movement that would flatten a building on land, all happening quietly beneath a mile of undisturbed seawater. Scientists call this pattern inflation and deflation, and it forms the entire foundation of how researchers try to forecast this volcano's next move. Every measurement from the bottom pressure recorders scattered around the caldera floor feeds into one continuous story. How high has the ground climbed, and how does that height compare to the moment right before the last eruption? Graphed over years, the shape looks almost like a slow, rising staircase that suddenly drops straight down, then starts climbing all over again from a slightly different starting point. For 2 full eruption cycles in a row, in 2011 and again in 2015, this breathing pattern behaved with impressive consistency. The ground rose to roughly the same height each time, then let go. That consistency is exactly what allowed Chadwick and Nuna to make their historic forecast, turning years of patient observation into a single, testable prediction. What nobody could be entirely certain of, though, was whether that same rhythm would hold forever. Volcanoes are shaped by forces far too complex to guarantee any pattern. Repeats exactly the same way twice, especially across many cycles stretching over decades. Right now, this lung has been slowly filling for more than 10 years straight, without letting go, and the height it has climbed to no longer matches any previous breath scientists have ever recorded, which means the comparison to a simple, repeating rhythm may no longer tell the whole story. There is a volcano on the opposite side of the planet that once behaved almost exactly this way, and studying it taught researchers a lesson that would end up explaining everything happening at Axial Seamount today. Somewhere on the internet sits one of the strangest science blogs in existence, dedicated entirely to guessing when one underwater volcano will finally erupt, updated by the very scientists trying to solve that mystery themselves. Bill Chadwick and Scott Nooner started the Axial Seamount blog to track their own forecasts openly, updating it whenever fresh data changed their thinking. Reading through years of old posts feels less like reading a polished scientific paper and more like watching two researchers think out loud, adjusting their guesses again and again as the volcano refuses to cooperate. Casual readers with no science background at all have followed the blog for years, drawn in by the sheer suspense of watching a real prediction unfold in slow motion. Early forecasts made shortly after the 2015 eruption pointed toward a possible eruption sometime around 2021 or 2022. That window came and went with the volcano still quietly inflating, nowhere near ready to erupt. The forecast shifted forward, then it shifted again. Each revision came with its own explanation: a slower inflation rate here, an unexpected quiet spell there. Small technical details stitched together into a running story that anyone following along could track for themselves. By late 2024, confidence had grown considerably. The ground had climbed to roughly 95% of its pre-eruption height from 2015, and researchers openly discussed a likely eruption sometime between the middle of 2024 and the end of 2025, a specific enough window to make headlines. Then inflation slowed. Earthquakes stayed unusually quiet. By October of 2025, Chadwick posted an update admitting the forecast needed pushing back once again, this time toward the middle or later half of 2026, a shift many long-time readers of the blog had started to expect. Reading these posts back to back, one pattern becomes obvious. Forecasting a volcano, even one as closely studied as this, is genuinely difficult. Chadwick has written openly about how nearly every prediction made since the 2015 eruption has needed revising at some point, simply because the rate of inflation keeps shifting in ways nobody fully anticipated, no matter how much data researchers gather. That kind of honesty matters more than it might seem. Most scientific forecasting happens behind closed doors, refined and corrected long before the public ever sees a number. Chadwick and Nooner chose instead to think out loud, in public, letting anyone curious enough to follow along watch real science stumble, adjust, and try again. Mistakes included, in a way most fields of research rarely allow the public to see. It also means something important for anyone following the volcano today. No scientist studying Axial Seamount is claiming certainty about exactly when it will erupt next. What they are certain of is something else entirely, something the blog itself keeps circling back to. The ground has now climbed higher than the exact level that triggered the last two eruptions, and the reason that height keeps climbing higher with every single cycle traces back to a lesson scientists first learned from a very different volcano, one sitting on dry land on the opposite side of the world, thousands of miles from the nearest black smoker or blind shrimp. Long before anyone fully understood Axial Seamount's rhythm, a volcano in Iceland quietly wrote the rulebook scientists would later use to explain it, decades before anyone connected the two systems together across two very different corners of the planet. Krafla sits in northern Iceland, a volcanic system that went through a dramatic, well-documented series of eruptions throughout the 1970s and early 1980s. Unlike Axial Seamount, Krafla sits on dry land, easy to visit, easy to measure directly with instruments planted right into the ground, without needing a research ship or a mile of open ocean between scientist and volcano to get close. Researchers studying Krafla noticed something unusual as they tracked its behaviour across many eruption cycles. Each time the volcano inflated and then erupted, the height it needed to reach before letting go crept slightly higher than the time before. The ground was not simply rising and falling back to some fixed, repeating level. The bar itself kept moving upward, cycle after cycle, in a pattern nobody expected when they first started tracking it. Think of it like a video game where the difficulty quietly increases every single level. Even though the rules on the surface look exactly the same as before, play the same level the same way you always have, and it no longer works because the target has quietly moved without any obvious announcement. When scientists eventually noticed a similar pattern, building at axial seamount, Krafla became the natural comparison. After the 2011 eruption, researchers measured the height the ground reached before the 2015 eruption, and it came out roughly 1 foot higher than the threshold that triggered the previous event. That matched the Krafla pattern closely enough that Chadwick and Noonan began factoring a rising threshold directly into their forecasts going forward. This single insight changed how scientists think about predicting axial seamount's future. A forecast based only on the old 2015 threshold would already be badly out of date. The real danger line likely sits somewhere higher. Exactly how much higher nobody can say with total confidence, since this kind of shifting threshold is difficult to measure precisely from a single volcano alone, especially one with only a handful of past eruptions to compare against. That uncertainty is exactly why the ground has now surpassed its old 2015 benchmark without erupting. Researchers currently estimate the true threshold this time might sit somewhere between 4 and 8 inches higher than that old line, based on how much the bar shifted between previous cycles, though even that estimate comes with real uncertainty attached. 4 to 8 inches might sound small. On a volcano this size, though, it represents an enormous amount of extra magma, extra pressure, and extra uncertainty stacked directly on top of a system that has already blown past every previous benchmark scientists once trusted completely. Spread that extra height across the entire caldera floor, an area wider than dozens of football fields laid side by side, and the total volume of extra rock and melted stone underneath becomes almost impossible to picture. Which leads to the moment that changed the entire story. The exact day the ground finally caught up to, and then passed, the height that used to mean an eruption was imminent. By the final months of 2024, every instrument watching axial seamount pointed toward the same conclusion. This volcano was close, closer than it had stood in nearly a decade. The seafloor above the magma chamber had climbed to roughly 95% of the height it reached right before the 2015 eruption. On a graph, the trend line looked almost identical to the months leading up to that historic, successfully forecasted event. Researchers presenting their findings at a major science conference that December described a volcano sitting right on the edge, primed and ready, with several colleagues in the audience openly expecting an announcement within weeks rather than months. Picture filling a bathtub almost to the very top, close enough that a single extra inch of water would send it spilling over the edge. That is roughly where axial seamount stood as 2024 came to a close, with scientists checking the water level almost daily, certain the tub was about to spill. Forecasts at the time pointed toward a likely eruption sometime between the middle of 2024 and the end of 2025, a window built on the same inflation-based method that had worked so well less than a decade earlier. Confidence ran high. This was, after all, the same volcano, the same instruments, and largely the same team of scientists who had already proven this approach could work once before. Then, almost as if the volcano knew it was being watched too closely, everything slowed down. Inflation rates that had been climbing steadily for years suddenly eased off in early 2025. Earthquakes, which typically ramp up dramatically as an eruption approaches, stayed strangely quiet, appearing in small, scattered bursts instead of the intense swarms researchers expected to see building. The bathtub, so close to overflowing just months earlier, seemed to simply stop filling, leaving everyone watching the data unsure what came next. For scientists who had spent years building confidence in this forecasting method, the pause raised uncomfortable questions. Had the underlying pattern changed? Was the magma chamber behaving differently than it had before past eruptions? Or was this simply the normal, messy unpredictability of a natural system finally reasserting itself after 2 unusually clean forecasts in a row? Some researchers began wondering aloud whether 2 accurate predictions in a row had simply been good luck, dressed up as a reliable method, rather than genuine proof the science had been cracked. Nobody had a certain answer. What everyone could agree on was this: the volcano had reached the exact edge of its old danger line and, instead of tipping over, had paused right at the rim, holding steady in a place it had never held steady before. That pause did not last. Over the months that followed, the ground began climbing again, quietly, steadily, eventually doing something it had never done before in the entire recorded history of this volcano. It kept rising straight past the line that once meant an eruption was imminent, into a height nobody watching this mountain had ever seen it reach in decades of careful, continuous observation. What happens once a volcano runs out of old benchmarks to compare itself to is where this story turns into something scientists are still trying to fully understand. December of 2024, a conference room in San Francisco, a room full of volcanologists listening as researchers laid out the case for something remarkable. Axial seamount, they said, would very likely erupt before the end of 2025. It was the kind of prediction that makes headlines. Reporters picked up the story within days. News outlets across the Pacific Northwest ran pieces on the underwater mountain about to blow, some breathlessly, some carefully, most repeating the same reassurance scientists kept offering. Nobody on land would be in any danger. Questions poured in from curious readers anyway, wondering whether this eruption might affect local salmon runs, nearby whale migrations, or the fishing boats that regularly cross the waters above the volcano. Then 2025 arrived, month by month, and the volcano simply did not erupt. January passed, then February. By spring the seafloor was still climbing, inflation holding fairly steady, but the dramatic burst of earthquakes everyone expected never fully materialized. In June, instruments did pick up something promising, more than 2,000 earthquakes in a single day, the kind of swarm that has preceded past eruptions. Scientists watched closely, wondering if this was finally the beginning. Within days, the swarm faded. Earthquake counts dropped back down to around 100 a day, sometimes fewer. The volcano once again had teased an ending and then pulled back. By August, researchers were candidly telling reporters that the rate of earthquake activity had been wavering up and down, with no clear trend pointing toward an imminent eruption. The volcano remained, technically, still on track to erupt sometime before the year ended. Nobody wanted to abandon the forecast entirely, but the confidence from that December conference room had clearly softened. Then, in July, an entirely different kind of drama unfolded. A massive magnitude 8.8 earthquake struck near Kamchatka, thousands of miles across the Pacific. The resulting tsunami waves rippled outward across the ocean, and as they passed near axial seamount, they triggered the automated alert system built to catch the earliest signs of an eruption. For a brief, tense moment, instruments flagged conditions that looked like the start of something big. It wasn't. The alert had been triggered by a distant earthquake's aftershocks in the water, not by the volcano waking up. Scientists studying the data quickly ruled out an eruption, a false alarm born from the ocean's ability to carry energy across thousands of miles in ways that can fool even the most carefully tuned instruments. By October, the forecast needed a full revision. Chadwick and Nooner pushed their estimate into the middle or later half of 2026, openly admitting that this was now the second time in 2 years their long-range forecast had needed correcting. Longtime followers of the blog had grown used to these revisions, but the pattern was becoming harder to ignore with every passing month. For a method that had worked so cleanly in 2015, watching it stumble twice in a row raised an uncomfortable possibility. Maybe the ground rising past its old benchmark wasn't a sign the eruption was close. Maybe it was a sign the entire rulebook needed rewriting. To understand why, scientists had to look at the one signal that refused to cooperate with everything else the data seemed to be saying. Every past eruption at axial seamount followed the same basic script. As the seafloor climbed higher, the ground grew increasingly restless, cracking and shifting under the strain of rising magma. Earthquakes multiplied. By the time the volcano finally let go, instruments were usually recording thousands of tremors within a single day. A clear, unmistakable drum roll leading up to the main event, loud enough that nobody watching the data could miss it coming. This time, the drum roll kept skipping beats. Through most of 2025, earthquake counts at axial seamount hovered around 200 to 300 a day, occasionally spiking toward 1,000, numbers far below what past eruptions produced in their final build-up. The June swarm of more than 2,000 quakes in a single day briefly looked like the real thing. Then it collapsed back down to barely 100 a day within a matter of weeks, as if the volcano had changed its mind. By the start of 2026, daily counts had dropped even further, sometimes staying below 100 for weeks at a stretch, with only occasional bursts of a few hundred breaking the quiet. Scientists compare an earthquake swarm to the creaking sounds a house makes as it settles. A little creaking is normal. A sudden escalating chorus of creaks usually means something structural is giving way. At axial seamount, the creaking kept starting and stopping, never quite building into the sustained roar researchers were listening for, leaving them to interpret a pattern that never fully finished its sentence. This mattered enormously, because seismicity had always served as the second half of the forecasting formula. Inflation told scientists how much pressure was building. Earthquakes told them how the rock itself was responding to that pressure, cracking, shifting, making room for the next surge of magma. When those two signals moved together, forecasts felt solid. When they drifted apart, as they had for most of 2025, the entire method lost some of its footing, forcing researchers to lean more heavily on inflation alone than they ever intended. Researchers have floated a few possible explanations, none confirmed. Perhaps the rock surrounding the magma chamber has grown slightly more flexible over time, bending instead of cracking as pressure builds, the way a fresh sheet of plastic bends before a brittle one snaps. Perhaps the pathways magma travels through have shifted since the last eruption, changing where and how the ground responds to rising pressure. Perhaps the relationship between inflation and shaking was never as tightly linked as two clean eruptions in a row made it appear. Bill Chadwick has written plainly that nobody currently has a confident answer, only that whatever is happening must somehow reflect a genuine change in how magma is currently moving beneath the volcano. Watching a scientist admit uncertainty publicly in real time is rare enough on its own. Watching it happen about a volcano that already produced one of the most celebrated forecasts in the field's history makes it even more striking. What makes this particular puzzle so unsettling is timing. The missing earthquakes are not simply delaying the eruption. They are unfolding at the exact moment the ground itself has already climbed past every previous warning line scientists once trusted completely, leaving two of the volcano's most reliable signals pointing in two very different directions at once. Somewhere in the data streaming back from axial seamount, buried in a graph most people will never see, sits the exact moment everything changed. For months, scientists had watched the seafloor climb steadily toward the height it reached just before the 2015 eruption. The number burned into the memory of everyone who had followed this volcano for years. That height had always represented something like a finish line, the point where past patterns suggested the ground would finally crack and let magma escape. Every fresh reading from the bottom pressure recorders brought that finish line a little closer, month after month, inch after careful inch. Sometime in the months following the stalled 2025 forecast, the seafloor reached that exact height, and then, instead of erupting, it kept going. Bottom pressure recorders on the caldera floor, the same sensitive instruments capable of detecting a rise smaller than the width of a coin, track the climb inch by careful inch. Scientists watched the numbers past the old 2015 benchmark with something between excitement and unease, aware they were now recording ground movement nobody had ever measured at this volcano before. Researchers refreshing the data that week described a strange mix of feelings, the satisfaction of watching years of patient monitoring finally reveal something new, paired with the discomfort of having no map for what came next. Picture running a race against your own personal best time, only to blow past it without slowing down, with no finish line in sight to tell you exactly how much farther you have left to go. That is roughly the position researchers found themselves in, watching a graph climb into territory with no prior data point to compare against, checking each new update the way a runner might glance at a watch with no course map to guide them. Today, the seafloor sits about 4 inches above that old 2015 line, based on the most recent measurements available. Some researchers believe the true threshold this cycle could sit even higher, following the pattern first identified at Krafla, where the danger line creeps upward slightly with every eruption cycle. If that pattern holds here too, the ground may need to climb several more inches before conditions finally match whatever level triggers the next collapse, a gap that could take months or longer to close at current rates. Nobody can say exactly how many inches that will take, or exactly how long it will require at current inflation rates. The instruments can measure height with incredible precision. They cannot yet tell scientists what height finally matters, a gap between measurement and meaning that no amount of extra precision alone can close. This uncertainty has turned axial seamount into something rarer than a countdown clock. It has become a live experiment in the limits of prediction itself, a chance to watch what happens when a system that seemed to follow clean, learnable rules for 2 eruptions in a row suddenly refuses to reveal where the next line actually sits. Every new reading from the seafloor now carries extra weight. Scientists refresh the data with a kind of anticipation that has little to do with fear and everything to do with genuine scientific curiosity, waiting to see exactly how much farther this mountain intends to climb before it finally answers the question everyone has been asking for more than a year. There is a particular kind of unease that comes from watching something behave in a way it has never behaved before, especially when that something has been carefully monitored for decades. Axial seamount has been under close observation since the late 1990s, watched more continuously and more precisely than almost any other volcano on the planet. In that time, it has erupted 3 separate times, each one giving scientists a fresh data point to compare against. 2 of those 3 eruptions followed a clean, predictable pattern, tightly enough that researchers built an entire forecasting method around it, a method that then went on to work exactly as designed, in public, in front of the entire scientific community. Right now, for the first time in that entire monitored history, the ground has climbed past its most recent danger line without letting go. Nothing in the volcano's recorded past prepared scientists for this particular moment. That distinction matters more than it might first appear. A volcano behaving unpredictably is not unusual on its own. Most volcanoes on Earth resist confident prediction entirely, shaped by too many overlapping, poorly understood factors to ever forecast cleanly. What makes this different is that axial seamount had specifically proven, twice, that it could be predicted, only to now break the very pattern that made those predictions possible. Few natural systems anywhere earn that kind of trust and then complicate it so directly, in full public view, with years of transparent data backing up every step. Scientists sometimes describe this kind of moment as a system testing the edges of its own known behaviour. Imagine a river that has flooded to roughly the same height during 2 major storms in a row, leading engineers to build flood defences based on that exact number. Then a 3rd storm arrives, and the water keeps rising past the old flood line, with no clear sign of where it will finally stop. The old data remains true and useful. It simply no longer tells the whole story, and everyone downstream has to wait and watch to learn what the new story actually is. For researchers who have spent entire careers building confidence in inflation-based forecasting, this moment carries real scientific stakes. If the method still works, just with an adjusted higher threshold, that would strengthen the case that volcanoes like this one really can be understood well enough to predict, reinforcing years of painstaking work. If the method breaks down entirely, that would be a humbling reminder of just how much natural systems can still surprise even the most carefully built models. Either outcome will teach scientists something valuable. That is precisely why researchers describe uncertainty like this as an opportunity rather than a failure, a rare, real-time chance to test the actual limits of a forecasting method under genuinely novel conditions, instead of simply assuming those limits from theory alone. Few natural experiments offer that kind of clean, real-time test, with instruments already in place and years of baseline data ready to compare against. Somewhere in that uncertainty, one new tool has already begun trying to answer the question the old method cannot. It works completely differently from anything researchers have tried at this volcano before, built not from patterns in the past, but from the physics of how solid rock actually breaks. On November 10th of 2025, an entirely new kind of experiment quietly began running on real-time data pouring in from axial seamount. Unlike the old forecasting method, built on comparing current inflation to patterns from past eruptions, this new approach starts from physics instead of history. It was developed by researchers Qinghua Lei at Uppsala University in Sweden and Didier Sornet at ETH Zurich in Switzerland. Scientists who originally built the underlying model to predict an entirely different kind of failure, landslides, rock bursts deep inside mines, and even cracking glaciers. The model treats an approaching eruption the same way an engineer might treat a bridge slowly failing under too much weight. As pressure builds inside a system, whether that system is rock, ice, or a mine shaft, tiny cracks tend to accelerate in a specific, measurable pattern just before final failure. Catch that acceleration early enough, the theory goes, and you can estimate roughly when the whole system will finally give way, using nothing but the shape of the acceleration curve itself. Researchers had already tested this model by feeding it old data from the 2011 and 2015 eruptions, checking whether it could have predicted those events after the fact. According to the scientists involved, the results looked promising, correctly identifying the timing of past failures using only the kind of data that would have been available in real time. That kind of retrospective success gave the team enough confidence to finally point the model forward instead of backward. Now, for the first time, the model is being pointed forward instead of backward, analysing live seismic and inflation data from the regional cabled array as it streams in, day by day, attempting a genuine prediction rather than a retrospective one. What makes this experiment especially unusual is how transparently it has been designed. Each monthly forecast produced by the model gets cryptographically sealed and publicly archived the moment it's generated, a digital fingerprint locked in before anyone knows whether the prediction turns out correct. That way, when the eruption finally happens, nobody can quietly adjust the numbers after the fact to make the model look better than it actually performed. This kind of built-in honesty is unusual even by the standards of a field already known for publishing raw, unfiltered forecasts in public. Researchers involved in the project have said plainly that the results will not be revealed or celebrated until after the real eruption occurs, since only that eruption can prove whether the physics-based approach genuinely works or simply looked convincing on paper, no matter how elegant the underlying mathematics might appear beforehand. If it succeeds, the implications reach far beyond one volcano off the Oregon coast. A model built from the physics of failing rock, rather than one volcano's specific history, could eventually be tested on volcanoes with no 20-year data record at all. Dangerous ones sitting directly beneath cities that have never given scientists the luxury of two clean eruptions to learn from. That possibility alone has drawn attention from researchers well outside the small community that normally follows axial seamount closely. For now, the model runs quietly in the background, crunching numbers nobody will fully trust until the mountain itself finally answers the question everyone is asking. Somewhere beneath axial seamount's caldera floor, rock is under more strain than at almost any point scientists have ever measured there, which raises an obvious, unsettling question. How much higher can the ground actually climb before something finally has to give? A question with no clean answer waiting anywhere in the data collected so far. Nobody knows the exact number. That admission alone says something important about where this story currently stands, coming from researchers who have spent years building the most detailed picture of any underwater volcano on Earth. Rock, even solid rock deep underground, behaves a little like an overstretched rubber band. Push it slowly enough, and it can absorb an enormous amount of strain, bending and flexing without breaking. Push it too far though, and the failure, when it finally comes, tends to happen fast, releasing built-up energy all at once rather than gradually, the way a rubber band snaps back the instant it finally gives. Scientists studying axial seamount believe something similar governs when this volcano finally erupts. Magma pressure builds beneath the caldera floor, pushing upward against solid rock that can only stretch so far before cracking. Based on the pattern observed at Krafla in Iceland, researchers suspect the true breaking point this cycle sits somewhere between 4 and 8 inches above the old 2015 benchmark, though that estimate carries real uncertainty, since it relies on a pattern built from only a handful of past eruptions. Even a small error in that estimate could shift the timing of the next eruption by months. Complicating things further, the ground has already climbed higher and stayed inflated longer than it did before either of the previous two eruptions without releasing that pressure. Some researchers have started to wonder whether an unusually long, unusually high inflation period like this one might behave differently than shorter cycles did in the past, perhaps requiring even more pressure before cracking, or perhaps building toward a larger event than anything recorded at this volcano before. Nobody is predicting anything unusually dangerous, Even a larger than average eruption at axial seamount would still pose no threat to people on land, given how deep and how far offshore the volcano sits. The uncertainty here is scientific, not safety related, a genuine gap in understanding rather than a hidden danger quietly building beneath the waves, worth studying purely for what it teaches rather than what it threatens. Still, the not knowing carries its own kind of weight. Every additional inch of inflation adds more stored energy to a system already operating well outside its known history. Scientists tracking the numbers describe a mounting sense of anticipation, less like waiting for a bomb to go off and more like watching a stretched spring coil tighter and tighter, aware that the release, whenever it comes, will likely happen fast and dramatically once the rock finally gives way. Nobody can say with certainty whether that release is weeks away or many months away, and that gap is exactly what keeps researchers checking the data every single morning. That uncertainty about scale, rather than about danger, is exactly why researchers keep returning to one persistent question from worried readers of the blog and curious strangers online alike. If nobody knows exactly how big this could get, should anyone living along the coast actually be concerned? Ask Bill Chadwick directly whether people on the Oregon coast should worry about axial seamount, and his answer comes back fast, simple, and consistent. No, that confidence is not guesswork. It comes from 3 specific, well-understood facts about how this particular volcano behaves, facts confirmed across 3 separate eruptions and decades of continuous monitoring. First, distance. Axial seamount sits roughly 300 miles offshore, a full day's journey by research ship from the nearest port. Whatever happens at the summit unfolds in nearly total isolation, far beyond the range where any surface disturbance could realistically reach a populated coastline with meaningful force. Second, depth. The volcano's summit sits nearly a mile beneath the ocean surface, crushed under pressure roughly 200 times heavier than what a person feels standing on a beach. That much water acts like an enormous cushion, absorbing and dispersing energy before it ever has a chance to reach the surface in any dramatic way, no matter how violent the collapse looks on the instruments recording it below. Third, and most important, the type of eruption itself. Axial seamount does not produce explosive, ash-spewing eruptions the way some famous land volcanoes do. Instead, it behaves more like the gentle, flowing volcanoes found in Hawaii, releasing thin, fast-moving lava through cracks in the seafloor rather than blasting material violently upward. There is no shockwave, no sudden displacement of massive amounts of water, nothing resembling the kind of eruption that typically generates a dangerous tsunami. Earthquake activity during an eruption, while intense in number, tends to stay extremely small in magnitude, nowhere near strong enough to trigger a major quake along the nearby Cascadia subduction zone, the genuinely dangerous fault line that keeps emergency planners along the Pacific Northwest coast up at night for entirely different reasons. Scientists have been careful to draw a clear line between these 2 systems. Cascadia represents real, serious risk to coastal communities, capable of producing the largest earthquake and tsunami the region has seen in centuries. Axial seamount represents something else entirely, a genuinely active volcano that happens to pose essentially no risk to human life, thanks to nothing more complicated than distance, depth, and the gentle nature of its lava. Confusing the 2, researchers note, only distracts attention from the fault line that genuinely deserves careful, ongoing preparation. There remains one purely theoretical scenario researchers occasionally mention almost in passing. If the volcano's flank were ever to collapse suddenly and catastrophically, displacing an enormous volume of water all at once, it could in theory generate a tsunami. Nothing in the current data suggests this kind of collapse is likely, or has ever happened at this particular volcano in its recorded history, and researchers treat the scenario more as a thought experiment than a genuine concern. So the ocean itself, combined with a fundamentally gentle style of eruption, effectively acts as the shield protecting the Oregon coast, turning what sounds like a dramatic headline-ready disaster into something scientists can study calmly, curiously, and without a hint of genuine alarm. Understanding just how safe this eruption truly is only makes the effort scientists put into watching it more remarkable, since nobody has to justify the monitoring with fear. They study it purely because it teaches them something no other volcano on Earth can. Nobody can simply walk down to Axial Seamount and check on it. So scientists send machines instead, robots built to survive conditions that would crush an unprotected human being in seconds, diving to depths no diver could ever safely reach. The most iconic of these tools is a torpedo-shaped autonomous underwater vehicle, roughly 20 feet long, that flies a carefully pre-programmed path across the seafloor, mapping the volcano's surface using sonar the way a bat might map a cave using sound. Unlike a submarine tethered to a ship, this vehicle operates completely on its own, diving for hours at a time, gathering data with no human hand guiding it in real time. Engineers at the Monterey Bay Aquarium Research Institute have used these vehicles to map axial seamount since 2006, building up one of the most detailed underwater maps of any volcano on the planet, precise enough to detect changes in the seafloor as small as roughly 4 inches. Every expedition adds another layer to that map, slowly turning years of individual surveys into a single, continuous record of how the volcano has changed over time. One particularly clever trick makes this mapping possible. The vehicles use something called terrain relative navigation, comparing what their sonar sees in real time against an existing map of the seafloor, allowing them to retrace an almost identical path year after year with incredible precision. Scientists can then subtract 1 year's map from the next, creating what researchers call a difference map, a picture that shows exactly where the seafloor has risen, sunk, or been buried under fresh lava since the last visit. Alongside these mapping robots, remotely operated vehicles tethered directly to a research ship and controlled in real time by a pilot on board handle more delicate work. These vehicles carry robotic arms capable of collecting rock samples, water samples, and even living creatures from around the black smoke events, all while a research team watches through cameras from the safety and comfort of a ship floating a mile above. Together, these tools have produced discoveries that reshape how scientists understand this volcano. Earlier this year, researchers using this exact combination of mapping and sampling robots uncovered 3 massive lava fields stretching along axial seamount's outer rift zones, each one covering between 25 and 39 square miles, with some sections more than 400 feet thick. Nobody had realized flows this enormous existed at this volcano, until robots capable of surveying such a huge area finally made the discovery possible, decades after scientists first began mapping this same summit by hand. Sending robots instead of people carries an obvious advantage beyond simple safety. These machines can stay down for as long as their batteries allow, repeat identical survey paths with a precision no human pilot could match, and operate in conditions that would end a human dive almost instantly. A single expedition can now cover more ground in a matter of days than early researchers could have surveyed across several entire careers. Everything these robots have mapped, sampled, and photographed over the years has slowly assembled itself into an unusually complete picture of what actually happens the moment this volcano finally lets go, a moment that begins, every single time, with the exact same violent collapse. Picture an enormous underground room, a magma chamber roughly the size of a small city, slowly emptying itself in a matter of hours after more than a decade spent quietly filling back up. That is essentially what happens the instant axial seamount finally erupts. As magma rushes upward and outward through fresh cracks in the seafloor, the chamber below loses the pressure that has been quietly supporting the ground above it for years. Without that support, the rock overhead simply cannot hold its own weight any longer. It falls all at once the way a floor finally gives way once too many supports underneath it have been pulled free. Scientists call this a caldera collapse, and at axial seamount it happens fast. During the 2015 eruption, the seafloor above the draining magma chamber dropped by roughly 8 feet within a matter of hours, an amount of sudden vertical movement that would demolish a building on land, all playing out silently beneath a mile of undisturbed seawater. Instruments recorded the drop so precisely that scientists could later plot the exact hour the collapse accelerated fastest. Think of a sinkhole opening on land, the kind that can swallow part of a street overnight when the ground beneath it hollows out. A caldera collapse works on a similar principle, except instead of a single street, an area of ocean floor stretching across several square miles drops all at once, following the exact outline of the emptying chamber deep below, a scale of collapse that would make headlines everywhere if it ever happened on dry land. Instruments scattered across the caldera floor catch this collapse in extraordinary detail. Bottom pressure recorders show a sudden, dramatic drop the instant the ground falls. Seismometers record a massive burst of earthquakes as rock everywhere nearby readjusts to the sudden change in support. Underwater microphones sometimes pick up the deep rumbling sound of rock cracking and shifting, a sound no human ear has ever heard directly, translated instead into data on a screen back on shore, hundreds of miles from where the collapse actually happened. What makes this collapse particularly fascinating to scientists is how precisely repeatable it looks, at least on the surface. The 1998, 2011, and 2015 eruptions all began in strikingly similar locations along the eastern side of the caldera, each one producing a broadly similar shape of collapse, almost like watching the same room implode in slightly different ways every time, using a slightly different combination of cracks each cycle. That consistency is part of what made this volcano so valuable for building forecasting models in the first place. A collapse this predictable in shape and location gave scientists a reliable target to study, year after year, expedition after expedition, slowly building the kind of detailed picture that most volcanoes on Earth never offer, since land-based eruptions rarely leave behind such a clean, undisturbed record to examine afterward. Once the ground finishes falling, the drama is far from over. Because the instant that chamber empties and the roof collapses inward, fresh lava is already rushing out to reshape everything above it, cooling almost instantly into rock formations that exist nowhere on the surface of the Earth. Formations that only make sense once you understand exactly what freezing seawater does to molten rock. The moment scalding lava from axial seamount touches freezing seawater, something happens that simply cannot occur anywhere on dry land, a transformation unique to the deep ocean floor. On the surface, lava flowing from a volcano cools slowly, spreading across open air, sometimes travelling for miles before finally hardening. Underwater, the temperature difference is far more extreme and far more sudden. Freezing seawater chills the outer surface of the lava almost instantly, forming a thin, glassy skin within seconds, even while the molten rock still glowing hot on the inside keeps pushing forward. That skin bulges, stretches, and eventually splits, letting a small blob of fresh lava squeeze out before it too gets chilled into another glassy shell. Repeat that process thousands of times, and you get pillow lava, stacks of rounded, bulbous rock formations that genuinely resemble a pile of pillows, sometimes only a foot across, sometimes several feet, layered on top of each other across enormous stretches of seafloor, each pillow marking one small pulse of the eruption that produced it. No lava on land forms shapes quite like this. The combination of instant surface cooling and continuous internal pressure exists almost nowhere else in nature, making pillow lava one of the clearest fingerprints scientists use to identify underwater eruptions, even in ancient rock formations that have since been lifted onto dry land by shifting tectonic plates over millions of years, long after the ocean that once covered them has disappeared entirely. Axial seamount is covered in these formations, layer upon layer built up from 3 known eruptions, and likely dozens more before recorded history began, a record stretching back centuries that no single expedition could ever hope to fully map. Earlier this year, researchers using autonomous mapping robots uncovered something that stunned even scientists who had studied this volcano for decades. 3 enormous lava flow fields stretching along the volcano's outer rift zones, each one covering between 25 and 39 square miles, with some sections piled more than 400 feet thick. Fields that size had gone completely undetected for years, hidden simply because earlier surveys never covered enough ground at high enough resolution to reveal their true scale. Only once robots capable of mapping dozens of square miles at a time were deployed did the full picture finally come into focus, proof that even a volcano studied this closely for decades can still be hiding secrets in plain sight. Within these massive fields, researchers found drained lava ponds, sunken depressions more than 300 feet deep, formed when a lake of molten rock partially emptied out from underneath its own hardened crust, leaving a collapsed shell behind like a cake that sank in the middle after baking. Some of these ponds stretched wide enough to swallow several city blocks whole, hidden beneath the seafloor until robots finally mapped their true shape. Every layer of pillow lava, every drained pond, every rippled channel across these fields tells scientists something about how, when, and how violently a past eruption unfolded, a permanent physical record written directly into the rock itself, readable centuries later by anyone with the right instruments to see it. And the entire time this violent, dramatic process plays out, mile after mile of reshaped seafloor, not a single person anywhere would ever know it was happening. Somewhere on a boat directly above axial seamount, at the exact moment the volcano finally erupts, a person standing on deck would likely feel absolutely nothing at all, even with an entire mountain reshaping itself a mile beneath their feet, the sea around them looking exactly as calm as it did the moment before. That single fact sits at the strange heart of this entire story. Beneath that boat, an area of sea floor stretching across several square miles is collapsing by several feet within hours. Thousands of earthquakes are rattling through the rock below. Fresh lava is pouring out fast enough to reshape the landscape permanently. And above it all, the ocean surface stays completely calm, undisturbed, giving away nothing. Bill Chadwick himself has said as much plainly. Even someone sitting directly above the volcano during an eruption would probably never know it was happening. The reasons come down to simple physics. A mile of seawater sits between the caldera floor and the surface, acting like an enormous shock absorber. The earthquakes generated by this eruption stay extremely small in magnitude, nowhere near strong enough to travel that distance and register as a noticeable shake on a boat. The eruption itself produces no explosion, no violent displacement of water, nothing resembling the dramatic surface disturbance most people picture when they imagine a volcano going off, even though the seafloor below is being torn open and reshaped at the exact same moment. Compare that to a land-based eruption, where ash can darken the sky for miles, where the ground visibly shakes, where entire communities sometimes need to evacuate with hours or even minutes of warning. Axial seamount offers none of that spectacle to anyone standing nearby, no matter how dramatic the collapse looks on the instruments recording it below. All the true drama unfolds entirely out of sight, a mile straight down, visible only through instruments built specifically to translate that hidden violence into readable data. This is precisely what makes the volcano such a valuable natural laboratory. Scientists can position an entire research ship directly above an active eruption zone, gather live data throughout the event, and never once worry about the kind of danger that would force a team studying a land-based volcano to keep a safe distance, watching from far behind a barricade while ash and rock fall from the sky. It also means the only way anyone beyond a small circle of researchers will ever know this eruption happened is through the data itself. Graphs, seismic readings, pressure recordings, and eventually, weeks or months later, freshly mapped lava fields that confirm exactly where and how the ground gave way, long after the ocean above has settled back into its usual, unremarkable calm. In a strange sense, this invisibility is part of what makes axial seamount so scientifically valuable and so quietly remarkable at the same time. One of the most violent, dramatic geological events on the entire Pacific Ring of Fire can occur in full force, reshaping miles of ocean floor without a single person anywhere on the planet feeling so much as a tremor, a contradiction that makes the volcano both perfectly safe and endlessly fascinating at once. And axial seamount is far from alone in hiding this kind of drama from the world above. For every underwater volcano scientists have carefully mapped and monitored, thousands more remain almost entirely unknown, scattered across the deep ocean floor without a single instrument watching them, quietly inflating in total silence. Researchers using satellite data have identified more than 43,000 seamounts across the world's oceans, nearly double the number known just a few years earlier, simply by looking for the subtle way a massive underwater mountain's gravity pulls the ocean surface slightly upward directly above it. And that number likely represents only a fraction of what actually exists. Some estimates suggest the true total could reach 50,000, perhaps even 100,000. Once smaller seamounts too subtle for current satellites to detect are finally accounted for. Newer satellite missions are already producing sharper images of the seafloor than anything available even a few years ago, adding fresh mountains to the catalogue with every pass. Only about 1/4 of the entire ocean floor has ever been mapped in detail using sonar from ships, the kind of precise, close-range mapping needed to actually confirm what a seamount looks like, whether it shows any signs of activity, or whether it might erupt again someday. The rest of the ocean floor remains, in a very real sense, uncharted territory, hidden beneath water too deep and too vast for humanity to have fully explored, even in an age of satellites and autonomous robots. This gap in knowledge occasionally produces startling, even dangerous surprises. In 2005, a United States Navy submarine travelling at high speed collided directly with an uncharted seamount in the Pacific, an impact serious enough to kill one crew member and injure most of the rest aboard. In 2021, another Navy submarine struck a different unknown seamount in the South China Sea, severely damaging its equipment. Both incidents involved advanced vessels using sophisticated navigation technology, colliding with mountains that simply did not appear on any chart available at the time, proof that even the most modern tools still cannot see everything hiding beneath the waves. Somewhere among those tens of thousands of largely unmonitored underwater peaks, other volcanoes are almost certainly behaving the way axial seamount has behaved for years, slowly inflating, quietly building pressure, following rhythms nobody has ever measured, because nobody has ever installed the instruments needed to watch closely enough, their entire story unfolding without a single witness anywhere on Earth. Axial seamount became scientifically famous specifically because it broke that pattern of neglect, chosen for intensive monitoring because it happened to sit close enough to shore and erupt frequently enough to justify the enormous cost of running 660 miles of cable across the seafloor. Most seamounts will never receive that kind of attention, left to inflate and erupt in total silence, unmeasured and unwatched, for as long as the ocean continues to exist above them, their entire eruptive history known to no one at all. That imbalance raises an uncomfortable question researchers rarely get to answer with confidence. If one of these unmonitored volcanoes were quietly approaching a major eruption right now, somewhere in the vast unmapped majority of the ocean floor, would anyone even notice before it happened? Or would the mountain simply announce itself the same surprising way axial seamount once did back in 1998? Buried inside years of earthquake data from axial seamount sits a clue that still refuses to fit neatly into any explanations scientists have tried so far. A puzzle piece that seems to belong to an entirely different picture. Every past eruption at this volcano built toward its final collapse with a rising chorus of earthquakes, thousands of tremors compressing into the days and hours right before the ground gave way. That escalating pattern became one of the two central pillars supporting the entire forecasting method scientists built here, alongside the steady climb of the seafloor itself. This time, that chorus has refused to fully arrive. Earthquake counts through most of 2025 hovered stubbornly low, sometimes barely reaching 100 a day, occasionally spiking briefly before dropping right back down again. The one genuinely promising swarm, more than 2,000 quakes in a single day back in June, collapsed within weeks instead of building into the sustained escalating pattern researchers were watching for, leaving the graph looking more like a series of false starts than a genuine countdown. Scientists studying the earthquake catalogue described the overall shape of activity as wavering, rising and falling in short bursts rather than climbing steadily the way it did before past eruptions, a pattern with no clean beginning, middle, or end. Compare it to a fire alarm that keeps chirping briefly before falling silent again, technically active, technically a warning sign, but never building into the sustained blare that would confirm something serious was truly underway. A handful of competing explanations have circulated among researchers, none of them confirmed. One idea suggests the rock surrounding the magma chamber might have become slightly more flexible since the last eruption, absorbing rising pressure through gradual bending instead of sudden cracking, producing fewer detectable earthquakes even as pressure genuinely builds underneath, hidden from the very instruments designed to catch it. Another possibility points to subtle shifts in exactly where magma is currently flowing beneath the caldera, changes that could alter which sections of rock experience the most strain, and therefore which sections produce the most shaking, redirecting stress toward parts of the volcano the instruments happen to cover less densely. A third, more unsettling possibility simply questions the entire premise. Perhaps the tight link between rising seismicity and an approaching eruption, so clean and reliable during the 2011 and 2015 cycles, was never quite as universal a rule as two clean examples in a row made it appear, a coincidence mistaken for a law of nature. Bill Chadwick has addressed this puzzle with the same blunt honesty that runs through nearly every post on the Axial blog. Nobody currently knows for certain what is causing this particular mismatch, only that it must somehow reflect a genuine change in how magma is currently moving beneath the volcano. Whatever the true explanation eventually turns out to be, the missing earthquakes have already accomplished something significant. They have forced an entire field of science to admit, openly and publicly, that the clean, elegant rules built from watching one volcano twice in a row might never have been quite as universal as everyone hoped. A lesson that will likely outlast this particular eruption by decades, shaping how the next generation of researchers approaches every volcano they study afterward. Somewhere, on some ordinary day that has not happened yet, an alert will quietly fire on a computer screen in an office in Oregon, ending a wait that has already stretched past a full year longer than anyone originally expected. Picture the exact sequence researchers expect to see, based on everything the 2011 and 2015 eruptions taught them. It likely begins with seismometers scattered across the caldera floor, suddenly registering a sharp spike in earthquake activity, dozens of tremors within minutes, then hundreds, then potentially thousands within a matter of hours, cracking sounds racing through rock that has finally reached its limit after months of steadily mounting pressure. Almost simultaneously, bottom pressure recorders positioned across the summit would begin showing something unmistakable. A sudden dramatic drop in seafloor height, the unmistakable signature of the magma chamber below finally emptying and the caldera floor collapsing under its own weight. Where the graph had shown a slow, patient climb, for more than a decade, it would suddenly plunge, a nearly vertical line marking the fastest change this instrument has ever recorded. Chemical sensors near the black smoke events would likely register their own shift, almost immediately afterward. Temperature and mineral content in the escaping water swinging as fresh cracks open and freshly heated fluid rushes upward through altered pathways underground. One more thread of evidence confirming the same story the pressure recorders had already told. All of this data would race back to shore at the speed of light, carried along the same 660 miles of cable that has connected this volcano to researchers for more than a decade. Somewhere in an office, a scientist checking their laptop, perhaps first thing in the morning, perhaps in the middle of the night, would see the numbers and immediately recognize exactly what they were looking at. A moment they had rehearsed in their minds countless times without ever knowing exactly when it would arrive. Within hours, word would spread through the small, tight-knit community of researchers who have spent years anticipating this exact moment. Ships would begin preparing for an expedition to the site, eager to gather fresh samples and direct observations before the lava has even finished cooling, racing against the clock to catch the freshest possible picture of a landscape still settling into its new shape. Autonomous mapping robots would be scheduled for deployment as soon as conditions allowed, ready to capture the freshest possible picture of a landscape reshaped within hours, before storms or shifting currents had any chance to disturb it. For the public, the moment would likely arrive far more quietly. A short press release, a handful of news articles, a brief flurry of interest before attention moved elsewhere. No evacuation orders, no emergency broadcasts, simply confirmation that, somewhere 300 miles offshore and a mile beneath the waves, a mountain scientists have studied for decades had finally done what everyone always knew it eventually would, right on schedule by geological standards, if not by the calendar anyone had originally guessed. And then, almost immediately, the volcano would begin doing exactly what it has done after every eruption before this one, quietly, patiently, refilling itself, starting the long climb back toward whatever height finally proves high enough the next time around, watched once again by the same patient network of instruments that caught it this time. Nearly 50 years have passed since scientists first traced the outline of axial seamount using sonar pings bouncing through the dark. In that time, an entire scientific career could have started and ended without a single dramatic breakthrough, If this particular mountain had behaved like most other volcanoes on Earth, quiet and unremarkable for millions of years at a stretch, it did not, and the patience researchers invested in watching it, decade after decade, quietly turned Axial Seamount into one of the most valuable natural laboratories on the planet. Consider what that patience actually required. Scientists had to build instruments capable of surviving a mile of crushing pressure for years without maintenance. They had to lay hundreds of miles of cable across an unforgiving seafloor, simply to receive data in real time instead of waiting for occasional, expensive ship expeditions. They had to return to the same site again and again across entire careers, slowly building a data record long enough to actually reveal a repeating pattern, funded year after year by grants that required proving the work still mattered. None of that happened quickly. The eruption that first proved this volcano was truly active occurred in 1998. The eruption that confirmed a repeating pattern occurred in 2011, 13 years later. The eruption that finally validated an actual public forecast occurred in 2015, 4 years after that, getting to the point where scientists felt confident enough to predict an eruption months in advance took the better part of 2 decades of unglamorous, continuous observation. That timeline offers a quiet lesson that reaches well beyond volcanology. Some of the most important scientific breakthroughs do not arrive in a single dramatic flash of insight. They accumulate slowly, built from thousands of small, careful measurements that only reveal their true meaning years or even decades later, once enough data has finally piled up to show a genuine pattern rather than a coincidence. A lesson that applies just as much to medicine, climate science and astronomy as it does to a single volcano off the Oregon coast. Researchers studying Axial Seamount today are, in a real sense, standing on the shoulders of scientists who spent entire careers gathering data they knew they might never live to see fully explained. Some of the instruments currently streaming live information back to shore were designed and installed by people who have since retired, never getting to witness whether the volcano would finally answer the question they spent their careers asking. That kind of patience has become increasingly rare in a world that often expects instant answers, immediate results, and rapid, dramatic breakthroughs. Axial Seamount stands as a quiet counterexample, proof that some of the deepest scientific insights only reveal themselves to those willing to keep watching, year after year, long after the initial excitement of a new discovery has faded into routine, patient observation, checking the same graph every morning without knowing when it will finally change. 5 decades in, that patience has still not run its course. The volcano, currently sitting higher than ever recorded, refusing to answer the exact questions scientists have spent years learning how to ask, is proof that even 50 years of careful watching has not yet taught researchers everything this mountain still has left to reveal, with no clear sign of when that final lesson will finally arrive. A mile beneath the Pacific, 300 miles from the nearest port, a mountain nobody can see is still quietly rising, exactly as it has been since the last time this story checked in on it, patient and indifferent to every headline it has already made, everything this story has followed, the sonar surveys that first found it, the chimneys pouring out water hot enough to melt lead, the strange creatures thriving in total darkness, the historic forecast that once made this volcano famous, and the current, unprecedented climb past every benchmark scientists ever trusted. All of it circles back to one simple, humbling truth about the ocean still sitting almost entirely unexplored beneath our own boats and beaches, closer to shore than most people ever stop to consider. Humanity has mapped less than a quarter of its own ocean floor. Tens of thousands of underwater mountains remain essentially unknown, unmeasured, unwatched, and even the single volcano scientists have studied more closely than almost any other place on Earth, wired with more than 140 instruments and 660 miles of cable, still managed to do something in the last 2 years that nobody expected, nobody fully predicted, and nobody can yet fully explain, despite 5 decades of patient, continuous watching. That is not a failure of science. It is closer to the opposite. Axial Seamount represents one of the very few places on the planet where researchers can watch, in real time, exactly how much confidence is earned through decades of careful observation, and exactly how quickly nature can still remind even the most well-prepared scientists how much remains genuinely unknown, no matter how many instruments are watching, or how many years the watching has continued, and no matter how many past predictions once proved correct. The volcano itself carries no opinion about any of this. It does not know it broke a forecasting method built from its own past behaviour. It does not know it has become a case study cited in conference rooms and blog posts around the world. It simply continues doing what it has always done. Magma slowly rising, pressure quietly building, rock stretching toward whatever point finally forces it to break, indifferent to every prediction ever made about it. What makes Axial Seamount worth understanding is not danger. Nobody along the Oregon coast needs to worry about this volcano tonight, tomorrow, or likely at any point in the foreseeable future. What makes it worth understanding is the reminder it offers, patiently, persistently, every single day the seafloor continues climbing, that this planet still holds mysteries close enough to reach, wired directly into cables running to offices on shore, and still capable of surprising the very people who have spent entire careers learning how to listen closely enough to notice, no matter how confident those careers had made them feel just months earlier. Somewhere beneath the waves right now, the ground is still rising, inch by careful inch, toward a height nobody can yet name, following a pattern that has already outgrown every rule scientists once thought explained it completely. And somewhere on shore, a scientist is checking the data again, the same way they have checked it nearly every single day for years, waiting to see exactly what this mountain does next.